Okay, so let's start. Thank you, Roberto, for this introduction and also for giving us the opportunity to teach this beautiful topic. So first things first, the aim of the course. The aim of the course is not teach you differential geometry, is not give you a fish, but is teach you how to study differential geometry. And in particular, we will focus on teaching you how to study this book. So you can consider this the textbook of the course. The structure of the course is very, I would say, not traditional. I mean, I haven't prepared slides. I have just commented out this book. So we will go through the book, and I will show you the important parts, and I will teach you partial notions in differential geometry extracted from this book. To be clear, today we are going to go through 150 pages of this book. So it will be very severely intense, and I ask you just to stay focused, to interrupt me, please, if you don't understand something. These are abstract notions, but this is differential geometry. Okay, so let's start going through this part. Okay, I'm not going through the index. You can see that there is something that we will skip. In particular, we will not talk about integration over manifolds. You should be able, after this course, to read this part by yourself. This is a beautiful part that we are skipping. I am just telling you that Daniele, that will teach you the last lecture, is a very specialist in this topic. So if before the last lecture you start reading this topic, you can ask him. And in the last lecture, Daniele will talk to you of a different part of differential geometry. Okay, we can start telling you the language. By differential geometry, we are studying a generalization of what you already have learned in calculus, that is partial derivatives and so on. As you know, calculus, you can do this in real variables, but you can do this also in complex variables. Corresponding, we have a real differential geometry, which is the topic of this course, of the first 4 lectures of this course, and we have also a different branch of differential geometry, which is called complex differential geometry. And also, I should add, maybe symplectic geometry. We are still deciding the topic of the last lecture. Okay, on the book. This book is the best book I have ever seen in differential geometry. This is not just one book. It is a series of supposed to be 4, but I guess the 4th one doesn't exist. And there are 3 of these books. This is the first one, and they are beautiful. I really suggest you go through all the 3 books. And in particular, their beauty is in the fact that they are very self-contained and introductory. I told you we are going to go through 150 pages. This would be, of course, impossible if this wouldn't be an introductory book. It means that every detail is worked out with proofs and so on. So we will skip a lot of things in these things. And as you can see, there are several appendices where you can find needed material, needed topics during the lectures. Okay, so I invite you also, if, for instance, if you have no idea what is topology, of course, in differential geometry, differentiable manifold is first of all a topological space, whatever this is. Okay, so if you don't know at least a bit amount of topology, you will never be able to understand really real differential geometry. So you can go through all the neat notions here. This is very useful because if you try to study topology, one of these topics by yourself using a specific book on topology, this is going to be very hard. You probably don't have the language for such an effort. This reminds me another question. The fact that I'm assuming I'm speaking to non-mathematicians. I mean, if you are a mathematician and you already attended any course in geometry, differential geometry, or istituzioni di geometria superiore, it would be called probably, then you already know everything we are going to face in this course. Okay, so I'm assuming you are not a mathematician, so forgive me if sometimes you will feel, some of you could feel offended because maybe I'm asking, do you know what is a linear map, what is a vector space, okay, and something like this. So please interrupt me, tell me yes, so I can be confident that I can go on and so on. And don't be shy on the other side if you don't know some of this topic. Okay, and this is the best part of the book. You have several problems, you have several exercises, and some of them are solved. I assure you, this can be a relief sometimes. Okay. Let's start. I skip the introduction because I'm talking too much. And let's start on the first part of this lecture. That is, we are going just to revisit notions that you already know, okay? We begin with a review of C infinity smooth functions on several variables, okay? You already know this. This is a function from Rn to R. Okay, C infinity, first of all, means there are partial derivatives, second partial derivatives, third partial derivatives, whatever derivative you like. Okay, C infinity means, is also called smooth. They are synonyms for us. And differential geometry is always assuming that everything is smooth. Whenever I will talk about something in this course, also if I don't specify this, we assume this is smooth. This is infinitely differentiable. Okay. Some notation. These are the partial derivatives. I'm just going through all of this very far, but please interrupt me if there is something that you don't know. You can see this is the annotated book. I'm telling you all clear, right? This means that the highlighted parts by this should be all right. That means if they are not, when you are going to study by yourself, please go through it and try to understand the notation, okay? And as I told you, C infinity and smooth are synonyms. Well, examples. For instance, this function, is it smooth? No, because there is no derivative in 0. This is just calculus 1. Okay, if you try to compute the derivative. Here there are other examples. Here there is a function which is C1. That means the first derivatives exist. They are continuous, but not C2. If you try to compute the second derivatives, and it is clear it is an integral function, so you can make the derivative first, but then you get the function that before I was telling you is not smooth, okay? Very good. What is a neighborhood? This is fundamental, okay? I will talk about neighborhood points. I will talk about open sets, and this is the part I was telling you about topology. Well, a neighborhood is just any open set containing the point. Be careful that you maybe are used to consider neighbors the ones defined by the metric, that they are circular neighborhood. You fix one point, you take a radius, and you take all the points in Rn which are within that radius from that point. Okay, that is a particular kind of neighborhood. But by neighborhood, we just need the notion of to stay close to a point. I fix a point, I take a neighborhood, means I am around that in an open set, usually implicitly connected, not made by two different parts. Okay. Well, maybe you know what is a real analytic function. A real analytic function means that when you take the Taylor polynomial, the Taylor series, this is converging. The punctual limit is giving you the same value as the function, and this usually for several functions happens within a certain called convergence radius, I think. Well, a real analytic function is, of course, infinity. This is a basic fundamental theorem, but it is very important to understand that a C-infinity function is not real analytic always. Okay, this is the main difference between complex analysis and real analysis, and will be the main difference between complex differential geometry, lecture 5 by Daniele, and this course. Okay, in this course in particular, we can assume, and it will be of fundamental importance, the fact that there are functions made this way. This is a function which is 0, 0, 0, constant equal to 0, and then becomes smoothing out into a positive function. Okay, this cannot happen with complex functions. Okay, because they are more rigid, because they are given, I mean, here you had zero derivatives. So if you have the function to be equal to its power series, the function must be 0 around this point. Okay, this is the problem. These are called BAM functions. This will give partitions of unity that are very useful in what we are going to do. There is a dedicated chapter to this, by the way. Yes.
So complex does not refer to complex numbers, just to this concept of...
well, refer to complex numbers because the functions involved. At the beginning, I was telling you, this is a function that you are used to this way. A complex function would be the analogous, just from Cn to C. Okay, so and these are the complex numbers. Okay, but when I say complex differential geometry, I mean all the framework that comes out doing the things we are doing in this course, but instead of considering a real vector space and real codomain of functions, just consider this one.
Also, a function space which considers analytic functions and not C-infinity functions.
Yes, yes, and the functions are analytic in that case. Yes, yes.
So you have a notion of complex differentiability, and this is much stronger than the differentiability. Automatically is yes.
Yes, the point that differential geometry means differential. Complex differential means complex differentiability, and this is very strong property. Okay, so this is just saying that in real differential geometry, sometimes just the Taylor theorem with remainder is enough. I mean, you don't have that the power series is convergent, maybe, but you have an estimate of the remainder and so on. Okay, another note. You see this section is not highlighted, and there is no sign here also. This means you can skip it. This means we will skip it into this course, but of course, when you are reading the book with your pace, with your time and so on, feel free to read it if you need. Okay, but for here we are just going to skip. And sometimes when we skip something, at the end we just have a note like this. This note is, I don't know if you can read it, yes. Summing up, every C-infinity function satisfies Taylor theorem with reminders, okay? At the end of every chapter, section, let's say not chapter, but I will call them chapter, there is a section with problems, okay? And sometimes I write something around the problem that means maybe a hint to solve that problem. On some of them, we will try to go through, not this one, because this is just the introduction. And just here, I changed the function. Here in the point A, I ask you to show that the function, not the given function, the tangent of x, is a diffeomorphism, but another function which is more important for given the times. This is the famous function used in neural networks in artificial intelligence. So this is why I'm putting it here. Okay, and okay, this is the this is an example which is important. So you see it is highlighted, and this shows you a very important thing in the differential geometry we are doing for the moment. In differential geometry, I don't know if this is surprising for you. I hope it isn't. But saying 0, 1 or saying 0, 2 or saying R is exactly the same. Okay, they are diffeomorphic. We will see what this means. They are equal in a mathematician brain when that brain is tuned on the real differential geometry station. Nice knowledge. And is this surprising for you? Or, I mean, in particular, saying that 0, 1 is the same as R. It is fine. Okay. And in particular, from this, you understand that we are not concerned for a notion of measure, of length. Okay, we are not considering length for the moment. This will be the topic of lecture 4, actually. This is differential geometry, not metric geometry, which is called Romanian geometry. Okay. This is the stereographic projection is a very important map, which here is used to show you that the open interval is diffeomorphic to all the line. Is very nice because you see you can show everything with a picture. So I will try to give you the idea that is behind the picture. I don't want to explain the formulas. Of course, you can make computation and you can find the formula and so on. But how does it work? Well, I want to give you a correspondence between points in the interval and the points on the whole line. Well, the correspondence is made this way. Fix a point here. That is, in this case, the center of this circle, 0, 0, 1. 3 coordinates, so you understand this is a sphere, actually, it's not just a circle. And you want to map this point to some point here. How do you do? You just take the corresponding point by vertical orthogonal projection on the sphere, and then you draw a line from here to here, and you land in another point. And you understand that as closer as you are to the point 1, number 1, as up you will go in the circle, and as far you will go on the real line. So you can see that this is a map from the open interval 0, 1 to all the real line. Okay, very easy, very, very geometric.
1 to 1.
1 to 1, exactly. And more than that, 1 to 1 is just referring to the set map, the map from sets. But this is, if you write it in coordinates, this is also a C-infinity map. It's a smooth map. You can have derivatives, okay? And Okay, this map has a very, very particular property. That is, this map preserves angles. Okay, and now I want to show you a picture to tell you how this works. That should be here. Okay. And I wrote, just as a warm-up, I want to convince you that this stereographic projection preserves angles. Okay, so what does it mean, preserving angles? This is a sphere, okay? And you have a vector here, a tangent vector, meaning a vector which is not going through the sphere, it's just touching the sphere. Okay, and you have another tangent vector, and on the sphere, these two vectors are making two angles, are giving you angles. How are these angles given? You have the North Pole, this point, which is the point from that you use for the projection. Okay, so the angle given by these two vectors can be thought as the angle you obtain in this way. We have to use some imagination here. Just take the plane that is cutting the sphere in this way. The plane is made by this vector and by the segment going through the sphere, inside the sphere, from the point you are projecting to the projection point, so the North Pole in this case. This is a plane, okay? And you cut the sphere with this plane. You do the same with the other part of the, with the other tangent vector. And I want to show you that this projection is sending this curve here, all these points, which is, they are giving you these angles, all these points are sent here to points forming the same angle. I mean, this angle is the same as this one. This is what we want to show, or what I want to convince you, okay? And in order to do this, I thought something this night, and I need to actually switch on the oh, that's better maybe. And you can take me while I show this, but I have to switch off the screen sharing so I can do it. Yes, it's the same. Okay, so I'm switching off the screen sharing because I'm now showing you something. Let me check if I can do this. Let's use an apple. This is the apple, okay? This way. This is a knife. Can you see this? Can you see this in big or?
Yes, we can.
Okay, so you should pin me probably because I'm looking at me in a small corner. Okay, so this is the North Pole. Okay, the North Pole, and let's say I have two tangent vectors in this point. Let's say the tangent vectors, I'm drawing two tangents here, okay? And the construction I was showing you consists in intersecating this sphere with the plane going through the arrow and the line going from the point to the North Pole. That means making a slice this way, okay? This is the plane, the knife is representing the plane, which is intersecting the sphere in the real sense. And then I do the same from here, and I go in this direction. Okay? Now, what I obtain when I remove, can you see this? Okay. What I obtain is a picture of a digon, you would call. Means a polygon with two sides, possible only on the sphere, of course, not on the plane. I mean, possible on the plane, but you just see one segment counted twice. And this digon has here the angle we are caring about, okay? And I could prove that this angle is equal to the same angle on the North Pole. I could prove by formulas, but I will just prove with a sentence that I always liked when I was studying physics, for symmetry reasons. This is a sphere, actually this is an apple, so no symmetry here, but if this was a sphere, for symmetry reason, the angle here at the top of the digon, at the North Pole, is the same as the angle here, okay? Now, the angle here, since this is the North Pole, is of two vectors which are parallel to the xy plane, okay? These two vectors are this way. And now, just trust me or think about it, that if I'm moving the plane that I'm using to project to, okay, if I project here or I project here, as long as the plane is horizontal, parallel to the xy plane, the angles are not changing. Just this is just a dilation, I would say, just a homotopy. Okay, I'm just changing lengths, but I'm not changing angles. And so, in particular, these angles will remain the same. Okay? Theorem proved. Apple sliced, and I go back to screen sharing. Questions on this?
Why is it important, this aspect? Was it just manipulation?
Oh, very, very good question. I'm happy you're asking me this. Why it is important preserving the angles? Because in complex differential geometry, this will imply that this map is holomorphic. Okay, so it has importance in complex differential geometry. In particular, this sphere means that this map is apart from the North Pole is a bijection. Okay, and you can, if I say that the North Pole actually is also going to a point, which is the point to the infinite, you can accept this. Okay, I am a mathematician, so I can tell this word infinite. And this map is giving you a correspondence between this sphere and the complex structure on C. This plane becomes C. And this means that if you take C, you add one point, and you make this, in this way, this space and you, but I'm going too slow. So another point in this annotation that I will make available to you, of course, the annotated chapters that we are studying. And at the end of every chapter, I put a too long didn't read section that means a summary. Let's say a summary of the things that I think are important in that chapter. Okay, so you can use this as a self-assessment, for instance, just to check if you got whatever was meant to get from the chapter. Okay. Yes, loading, please. Okay. Okay, now, this is the big leap we are going to do, but it's very, very easy. You know what is a vector? Please tell me yes. Okay. And this is an element in R3. Okay. And you know that you can do the directional derivative. You know what is the directional derivative? Means taking the derivative not in the direction of x, y, z, or whatever, but just in the direction of that vector. Okay. And okay, this is later. I want first I want to tell you something here. Our goal in this section is to find a characterization of tangent vectors that will generalize. And what does it mean, will generalize? It means the following. When you say, let's go back to this vector. When you say you have this vector, you understand that you are assuming you have chosen a basis. There is a basis for R3. Chosen, I mean, from the beginning. Now, of course, there is something called the canonical basis on R3, but since this is defined as the product of three real fields, and so you have the vectors that are 1, 0, 0, 0, 1, 0, 0, 0, 1, okay? But if this vector is appearing as a quantity by itself, maybe because it's a force field, it's an energy, it's a magnetic, electromagnetic field or something like this. This vector is defined not because it is 1, 2, 3 by its coordinates. It's defined in another way. And it's defined also when you change the basis. Okay, this is expressed by this fact. This is a vector. I wrote B is B, okay? Defined in some way. You put a frame behind it, and you have coordinates, which is, in this case, more or less these numbers. Then you can change your frame, but the vector is still the same. It's not moving, okay? The frame is moving, and in this new frame, in this new basis, the vector is changing numbers, okay? When you do analysis in Rn, you are implicitly, from the very beginning, since you are 3 years old, you are choosing the canonical basis, okay? And x, y, z are with respect to that canonical basis. Manifolds will look like Rn, but without this particular choice of basis. Okay, we will be more precise on that. So, and this means that if you want to define a vector in this language, when the vector is represented with coordinates, you probably know better than me this kind of situation, this kind of language, you have to show that the rule giving that coordinates is changing according to the change of basis, which means usually with respect to multiplication by the coefficients of the change of basis matrix or its inverse and so on. Okay? And all of this doesn't apply only to vectors, also to concepts like maps from vectors to vectors. For instance, the cross product in R3. The cross product is well defined. Take two vectors and take the third vector, which is orthogonal with a suitable length given by the product of the length of this thing, right? Of the angle. And this is a well defined concept, okay? But you can express it in coordinates. And this expression will change, since this is a well-defined concept, will change in a certain way, which is more complicated than just using the single transition matrix, because this is something using 3 vectors, taking in input 2 vectors and giving as output 1 vector, will be called the tensor of type 1, 2 in differential geometry language, okay? Okay. Now, here there is the definition of directional derivatives. I will often ask you if I can skip this, okay? And if I don't get an answer, I will assume the default is yes, okay? Can I skip the definition of directional derivatives for a function from Rn to R? Okay. Well, I just want to point out that at the end, you have a formula, which is this one. I'm skipping the proof, but I need that you remember also for notation this formula. The derivative in the direction of the vector b is given by, this is, we can call the scalar product between the vector b and the gradient of f. Maybe you know this notation. This is the total derivative formula. I don't know how it is called. Well, first step, this means that you have an operator acting on functions. What does it mean? You have the notion of derivative in a certain direction, which is giving you a way to act on functions. Okay? So this means that you have a map. This derivative along V is taking a function on Rn and is giving you its derivative in the direction of V. V is a vector in 1 point, okay? So the result is just a number. Okay, is this clear that derivatives are this way? And this means in particular that given V, I have such a derivative. Okay, so I have a map, let's say, from V to the derivative along V. Okay, just take this in mind, this abstraction, and now we will see what's happening. Now I want to point out something. This map, the derivative of a function along a certain direction. Can you imagine 2 functions having the same result by this map? Very easily. What are they supposed to satisfy? 2 functions in order to have the same derivative in a certain point P. It is enough that they are locally equal. That means that around P, the functions are the same. Okay? If 2 functions around P are the same, it doesn't matter what they do in other points, far from P, because the derivative is local concept. Okay. Well, this is expressed by this sentence. As long as 2 functions agree on some neighborhood of a point P, okay, they will have the same directional derivative at P. And this suggests, now this sentence, do you understand this sentence? This suggests that we introduce an equivalence relation on the C infinity function. Is this clear to everybody? Equivalence relation? Fantastic. Are you sure? Don't be shy. Perfect. So this means that one function and another function, two functions from Rn to R, I will call them equal in some sense, given by this equivalence relation, if f is equal to g around P. Okay, this is formally given in this text, but this is the idea. Two functions are equal if they are equal around P. Well, at this point, I can't anymore call them functions because one of them is a set of several functions, all equal around P. So I call this set of functions, they call the equivalence class, I call it the germ of the function in the point P. Okay? And so what I'm telling you is that what I told you before was that the derivation along a vector B is acting not on C infinity functions on Rn, but on the germs of this function. Okay, and the germs are denoted by this symbol. Just putting a P here, where V is a vector in tangent in P to Rn. Okay, tangent vectors, we think of them applied in a point. And so this map is made this way. Okay, so I'm now interested in the set of this kind of maps. So I'm interested in maps from germs of functions to real numbers. Okay, I'm abstracting, but everything should be very clear, at least every passage. I mean, remember, you are not supposed to memorize all that I'm telling you now, okay? You just have to understand every single passage. Now we are interested in the set of maps from germs of functions to R, okay? And okay, let me check here. No.
Sorry, what does NP mean? Means next to that.
Okay, right. NP means next page. It means that on the next page, I inserted a page not from the book, as you can see, with something relevant. Okay, and in this case, the next page is commenting this sentence. That is, what is an algebra over a field? That is a vector space with a multiplication map. Okay, and in the next page, I'm telling you that it's very important to be able to abstract important properties from the spaces we are interested in. This space of derivations, they are maps. Of course, they are a vector space, okay? Because a map, you can multiply for a number and you can sum two of them. But they are more. You can also multiply two maps. And so they have an additional structure. So a mathematician would ask himself immediately, okay, what are the general properties which are satisfied by a vector space when, other than the sum and the scalar multiplication, there is also a multiplication, an internal multiplication, okay? This is something more, an additional structure, okay? And since I'm interested in a set with this structure, I will ask myself, are there properties of this kind of spaces, not only this one that I'm studying, but in general, properties of this kind of spaces that I could use to study this particular instance of the structure? And so, first thing, you give it a name. And you call this, okay, I will call this an algebra. An algebra is a vector space over a field with a multiplication map. You see, we build on already known topics. An algebra is a vector space. If you don't know what is a vector space, of course, you have to stop and study vector spaces first, and then you can go to algebras. And when you put additional structures on an already existing structure, you ask for compatibility. I mean, no reason in putting a multiplication when this multiplication is not distributive with respect to the sum, for instance. This is a very reasonable assumption, okay? And so you will ask something like this. And also, you have another multiplication, the scalar multiplication, and it would be nice if doing this would be equivalent to doing this. Structures on top of other existing structures, you ask for compatibility. Otherwise, they are just two different structures. I mean, you can study them separately, right? You can study the multiplication and the vector space if they are not related, okay? This will be very important in the next lecture because we are now studying manifold. That is, we will see what, and then in the next lecture, we will study what happens when the manifold is also a group. That is, there is a sum, there is a product, okay? And this is what is called Lie group, assuming that the manifold structure is compatible in some sense to be cleared off with the multiplication. You were asking something?
So you're adding a multiplication map with these three features.
Yes, yes, in an axiomatic way, in this way. In this case, for derivations, in order to state that derivations are an algebra, I have to check whether these three axioms are satisfied, okay? Okay, I'm really trying to let you know how a mathematician would argument. All these things I'm telling you are trivial for a mathematician. I would never specify them to a mathematician, okay?
In principle, these three and not the first two, or not adding a fourth.
Yes, yes, of course, of course. This is the way all the world thinks about an algebra. If you say, is this an algebra? These are the properties. Okay. Okay, this already told you everything. Okay, so we say that for each tangent vector, we have a map this way. This is not just a map from this space to this. This is a map which is a derivation. What does it mean, a derivation? Well, it satisfies the product rule, the usual classical product rule of derivative of function. That is this one. Trust me, you can verify it, but of course, this is the derivative formula. You already know for functions of one variable, it works also for the directional derivative in a specific direction. Okay, so from this moment, since we are interested in this kind of objects, we give it a name and a symbol. So the derivations at P are the map this way, satisfying this property. Okay, and are denoted by this symbol. And what I told you up to now is that a tangent vector gives you a directional derivative, which is a derivation at P, this new derivation, with this new definition. Okay. Now, whenever a mathematician finds such a statement, every derivative along a vector is a derivation at P, it is very natural to ask if the opposite is true. Are all the derivations in a point given by the derivations along a certain vector? Okay, is not only the question clear, but that is very natural to ask this. Okay, and this is asked here. Is the opposite true? And here you can find a very big arrow taking you to the answer. Yes, this is the answer, but please trust me, because otherwise we sleep here. And yes, there is another arrow. Okay. And all these pages which we are skipping are telling you that the tangent vectors are nothing more than derivations at the point P. Tangent vectors in a point are derivations. R means there is a one-to-one correspondence between a tangent vector at P and maps from C infinity, sorry, always the wrong C. Please disappear. Okay. From C infinity.
So, apparently very different objects, but
completely different objects. Okay, so a tangent vector, which is up to 3 minutes ago was an arrow or just a set of numbers giving a basis, are now maps from an equivalence set, from equivalence classes of functions satisfying certain property, that is to be a derivation, that is satisfying the derivative property, okay? Which is very natural because they are tangent vectors, and we started with making the derivative along that direction, okay? Remember when I told you that for manifolds, we don't have a basis, a preferred basis. And so this means that for manifolds, we can't define a tangent vector as choose a basis and take these numbers. But if we are able to define smooth maps on a manifold, then after that we can define tangent vectors in this abstract way. So we are looking for, and we found actually, a new formulation of tangent vectors for vectors in Rn that you have never met before, because maybe when you have the basis, life is easier this way. Or I don't agree on this, because this point of view is very useful also in Rn, of course. But maybe because it is a little bit more abstract and something like this. Okay? From now on, we will make this identification. For us, from now on, please forget arrows. A tangent vector is this. Okay, I will say tangent vector means a linear combination of partial derivatives, which is, if you prefer, the derivative along the vector v. Okay, but this is useful because it expresses very clearly the dependence on the chosen basis here. Okay, what is a vector field, and what's the time actually?
20 to 4.
Okay, it's very, very slow, but
Sorry, maybe we're interrupting you.
no, it's that. Okay, vector fields. I will just show you a picture. I know I told you forget arrows. Well, for vector fields, arrows are useful. Okay. In fact, here I wrote not really. Okay. Okay, this is a vector field. You know what this means? It means that in this point, this is a function giving, a vector field is usually denoted this way by x. This is a function from Rn, giving for every point of Rn a tangent vector in that point. Okay? The tangent vectors are in Rn are this way, okay? But this is in some sense the tangent space to Rn, in the sense that we will see. And in fact, you see, these vectors are put in different points. Okay? And in particular, a vector field in a point is an arrow, is a tangent vector. Tangent where? In that point. So this is an element of the tangent space in P. Okay? And of course, you can, since a vector field is giving for every point a tangent vector, this means that when you do the vector field computed in a point, you obtain a linear combination of the partial derivatives in that point times coefficients, right? Coefficients AI. And this means that when the point P is changing, these AI are functions from Rn to R. So at the end, a vector field is just given by a linear combination where the linear coefficients are functions, not just numbers. When you compute them in a point, then they become numbers. Okay? Please notice that in this way, I can take a vector field and multiply it by a function. What does it mean? Well, it means that I will just take the value of the vector field in that point, and I will multiply this vector. This is a vector now, a single vector. I can multiply it by the number f of p. Okay, so this is a definition of the multiplication of vector fields by functions. As you can guess, when you have a set, and on the set you can multiply by functions, if you can multiply by real numbers, then that set is close to be a vector space, right? If you can multiply by functions, well, functions are not R or C, are not a field. I don't know, you know, vector spaces over a field, right? Functions are not like that. So you give this kind of structure another name. We call that a module over the functions, because the functions have a structure which is the structure of a ring, not a field. But we are going far this way, just to tell you the reason why there are these sentences. Okay. New structure, new morphism. Now, let's go further ahead. Vector fields are derivations themselves. What does it mean? Here I'm telling you exercise. This one. Read this sentence. If X is a vector field on U, and if F is a infinity function, I can define a new function which is XF. Can you guess this definition? It is a very good exercise when you read a book like this, trying to do things by yourself, because this way you really understand. So you reach this point, you read, we define a new function XF on U by, you stop, you don't read ahead, and you try to put things together by yourself. And a very clever professor of mine, when I was doing my university in Rome, used to tell us that usually things, you can put together things, all the ingredients you have, in just one way. And that one way is the way that works. Actually, he used to say, se c'è un po' di giustizia a questo mondo, le cose sono così. It was Enrico Arbarello, very, very great professor. Now, let's put things together here we want to define a new function, okay? So in order to define a new function, xf should be a function. So you should tell me what is its value in a point. What is its value in a point? Well, you have a vector field, meaning that given a point gives you a vector. So take this vector, and this means that you have a tangent vector, right? What are tangent vectors? Arrows. Derivations at the point. Derivation means that they can take as input a function. Oh, here we have a function. Oh, what a chance. So I take this function, I take the directional derivative of that function in this way, and I obtain a number. But what I was looking for? I was looking for a function. And this is, I put a point, and I obtain a number. This is a function, right? Okay, so this is the answer. Okay, and this is just this definition. What I want to say with this is that this seems a huge amount of notions. Okay, in 16 pages, there are already 10 new definitions of concepts, but all of them are very natural concepts. Okay, I'm not telling you anything new. Okay, just I'm putting things in a smart way so that they can work also in a different situation that we will see. Okay, and you know what? This action on function, since it is given by directional derivative, can you guess what happens when I take the function associated to the product of two functions? Well, you know what? It's a derivative. So will be the derivative times g plus this times. I mean, of course, it's a derivation. Okay. So what means this? That we have this correspondence, and in this correspondence, the product of two functions satisfy this rule. That is a new derivative rule, right? And in general, you call derivation every map on an algebra. This is why I was telling you what an algebra is, just satisfying this product rule. Okay, so this means that the set this means that a vector field takes a function of Rn for the moment, of U actually, takes a function on an open set U, and gives you a derivation. Careful, this is not the same as before, a derivation at a point. This is a derivation of the C infinity functions. Okay, a derivation of this algebra means a map from this algebra to this algebra. A vector field is a derivation in the sense that it transforms function to functions, not functions, not germs of functions to numbers. Okay, so the big picture is the tangent vector at a point is a derivation at a point. Oh, what a surprise. The tangent vectors given by a vector field that is several tangent vectors in several points gives several derivations at a point that are actually derivation in this. Field is a derivation, but is every derivation a vector field? You guess what? Yes, it is. So we have a new way of looking at vector fields. Okay. Okay, yeah, we have problems, and I was assuming we were going to do together a problem for each chapter, but this is of course not possible because of time. The two-on the red section is very dense. You will use it and check the next chapter. Okay. So now this is a linear algebra actually, and I will just tell you the notation, the terminology, but I'm assuming that you already know what linear algebra is. I mean the construction. In particular, what I need is the notion, very important notion, of dual vector space. I have a vector space in abstract, think to Rn if you like, but we do not need this. And actually, we will use abstract vector spaces. And I can take linear maps on these vector spaces. I can take the set such that F is linear. Okay, and is this set here, the homomorphism in the sense of the vector space from the vector space to the real numbers. This is called the dual vector space. Okay, the dual vector space, there is a nice notion of dual basis. If you start with the basis for V, for the original space, vector space, then you have a dual basis. How is this dual basis acting on vectors? Well, it's just taking the coordinates. So alpha 1 will take the E1 coordinate of every vector, and so on. So it's a map from the vector space to R. Okay, this is called the dual basis. And please notice again that everything I'm telling here is depending on this choice of this base. You don't have a dual basis. You have the dual space, of course, but the dual basis it is in relation with the original basis, of course. Okay. Permutation, we can skip them. Now, a linear form, let's say, a map from V to R, or equivalently, an element of V star, here denoted by this symbol, actually, okay, but I prefer to use this symbol here, which is the same for the tangent space, is a special case of a more general notions, that is the multilinear maps. I mean, you can have also a map from V times V to R, and asking for this map to be linear, right? Of course, linear means linear with respect to each copy of the vector space. This would be a bilinear map. And you can have also a trilinear map, and so on. Okay, and these are called multilinear maps, multilinear functions. Okay, what are we using them for? Well, we are using them for a very important thing. We are using them, in particular, we are interested in the ones that are alternating. Alpha, a map here is called F. F from V times V in R is alternating. Can you guess the definition? Tell me. Somebody tell me the definition. Hurry, the times. Meanwhile, I will change the pen. What is, in your opinion, an alternating multilinear map? Can you just tell me? Very good. Is this very natural, right? And what if I add another v here? Then okay, let's call them this way. What should happen in your opinion?
Minus V3, V2, V1.
V3, V2, V1. Let me check. Oh, yes, but and it's only this?
No.
Okay, so it's alternating if whenever I switch a couple of them, the sign changes. Okay. In particular, this means that if I switch V2 with V1, and then V1 with V3, that means I obtain V2, V3, V1. The sign was switched twice, and so it remains the same. Okay.
It looks like the Ricci symbol.
Sorry?
It looks like the Ricci symbol when you oh, not the Ricci, sorry. When you compute the cross product and then you look at
Exactly.
the permutations.
Well, the Ricci symbol is
the
just
the Levici Vita, maybe it's called in some books, maybe symbol.
okay. All of these are example of tensors. In particular, if this alternation appears, it means that they are differential forms.
Mm-hmm.
So this example, you are referring to the Ricci form, probably, which is a differential form. So yes, exactly. It looks like, because this is what we're talking about. Okay, at the end of the course, you should be able, in particular, to understand the relation between what you call the Ricci symbols, which is the coordinate way of looking at these concepts with respect to the coordinate-free way that I'm trying to tell you. Thank you very much.
Okay, thank you.
Okay, so we are interested in alternating multilinear functions, okay? And this is this part. We are especially interested in the space of alternating multilinear function, so interested that we give it a name and symbol, okay? The name is alternating K tensors or K covectors or multi-covectors of degree K on the vector space. And the A stays for alternating, of course. Okay? Yes. AK of B is better called them maps, but they are the maps from V times VK times to R, which are multilinear and alternating. Okay. Okay. Just a notice, if I have a map from V times V to R, not alternating, okay? Can you make it alternating? Turn it into alternating. I mean, use it, not turn it. This is not alternating, so you can't turn it into alternating. I mean, use it to build a new multilinear function which is alternating. You should tell me what is this using alpha. Can somebody answer this? 10 seconds to answer before the solution appears. Okay. Well, of course, there is more. I don't know if this is what you call the antisymmetric part, but yes. Okay. Do you agree that this is antisymmetric? Okay. And of course, if you here take plus, you obtain the symmetric part. For the moment, we are not interested. Of course, we are interested also in that kind of tensors, but for the moment, no, just in alternating ones. Okay, this is the point of this section, that you have alternating operators. That is just this thing. Okay. Well, we will use the notion of tensors, and so this is what is a tensor product. It's just a product of two linear functions. I mean, you have a k linear function and L linear function. The tensor product is just a map which is k plus L linear. Okay. So in particular, the tensor product of two dual vectors will give a bilinear map. Okay. There are a lot of things to say here, but I'm assuming that we are confident with linear algebra. This is just a note. Okay, now a point. I just told you that if you have F and G multilinear, we have a product, F tensor G, the pointwise product, when you see them as a linear map, okay? But sometimes, not sometimes, always, when these are alternating, we would like a product which is inside the space, meaning we would like the product to be alternating itself. And this is not alternating. Okay? So how would you define a product which is alternating? Well, start from here and make the, how do you call the antisymmetric part, right? And do the antisymmetrization. So do the same as before, which is denoted by this symbol. Okay, and this is a new product, right? It's not the tensor product. It is the tensor product, but then followed by the antisymmetrization. This is what is called F wedge G. And this symbol, the wedge product, will live with you forever from now on, because we will use it always. I mean, when you have two differential forms, you put a wedge between them and you obtain a new differential form, okay, in this way. Okay, now a point, maybe there is, yes, here there is an example, let's say an exercise. Take F, which is alternating of rank 2, and take G, which is alternating of rank 1, which is means no symmetries, of course. Okay, and now I'm asking you to compute F wedge G. That is the wedge product between a 2 form and a 1 form. First things should act on 3 vectors, right? Because 2 vectors of input here, 1 vector of input here. So you should tell me what is this evaluated on 3 vectors. Okay. And this acts on 2 vectors, this acts on 1 vector. You have just to alternate every vector here. So you will take F of V1, V2 times G of V3. Plus or minus, we will decide, F of V1, V3 times G of V2. What do you think? The sign here is plus or minus? It's minus because I just switched two of them, and so on. Okay. If you notice in this, at a certain point, you will have also minus f of v2 v1 times g3 gv3, right? But this is alternating, so this is plus v1 v2, so it is exactly the same as this. So you will count twice this point. This is the reason why in the actual definition you have this normalization factor. Okay, that 2 is 2 factorial, the number of possible permutations on 2 elements. Okay, just the point. This is anti-commutative. Well, you see, sometimes you have a section this way. Well, associativity of the wedge product. I told you this book is giving you every detail. You have a product. Would you like a product which is not associative? I mean, associative means that you can write 3 times 5 times 7 without using parentheses. Okay, that should be absolutely forbidden by the law, a rule which is not associative. Okay, so you ask, is the wedge product associative? Otherwise, I will quit my job. Yes, it is, and I am writing you good behavior as expected. Okay, actually, it is not forbidden by the law to be not associative. There is a field, there is a multiplication rule which is called the Ortonionic multiplication rule. The octonions, which are the complex numbers over the quaternions. You probably know quaternions before you are engineers. Hmm? No. And octonions, have you heard about that? Well, do the complex number construction over quaternions, you obtain octonions, which are unfortunately not associative, which is the reason why the 7-dimensional sphere is not a Lie group. I'm telling you all of this just to fascinate you with what is in this world, and something that you will probably never know, because I mean, you have a limited time to study these things. But I mean, they are beautiful. Okay, I do a lot of octonionic geometry. This is why I'm telling you this. No highlighting here. Very good, very good. We can skip this. Okay, we need this definition. When I have an alternating form of degree k, and I can take all the alternating forms. Okay, all the alternating forms are naturally divided in subclasses of the alternating forms of degree 1, the alternating forms of degree 2, the alternating forms of degree 3, and so on, right? That means if you have a basis, if this is a basis of the dual space, that is, each of them is an alternating form of degree 1, that means a map from V to R, alternating, because every linear map in one slot, in one input, one vector is alternating. Then you have a basis for the degree 2 alternating forms, which are, well, if this is a basis, this means that alpha 1 wedge alpha 2 is an alternating 2 form, right? And it is not surprising that all the set made this way, alpha 1 wedge alpha 4, and so on, and then alpha 2 wedge alpha 3, alpha 2 wedge alpha 4, and so on. In this way, you obtain a basis for the degree 2 alternating forms. Take 3 of them. I mean, with the wedge product, you can now generate every k-linear alternating forms. Okay? And just to give you a mnemonic, I mean an argument to force you to follow me, besides the fact that we are talking since 2 hours now, these are the famous the x, the y, the z. This alpha 1, alpha 2, alpha 3 corresponds to the differentials. These things that you use in derivatives and in the integral sign, and nobody gave you a meaning to this. I mean, it's the infinitesimal displacement of a vector when you pass from x to x plus dx, okay? This is, I mean, this is a language of 1 century ago. And differential geometry in particular gives a meaning to these symbols, and we are arriving to that. Okay, so these are just the x, the y, the z, and so on. And this means in particular that differential two forms in R3 are generated by the x wedge the y, the x wedge the z, the y wedge the z. Okay, these are two forms. I don't know if you already used these symbols with the wedge. Have you ever met this symbol wedge? No? Okay. And okay. This is a way to generate two forms. And of course, you have 1-3 form, which is the x, the y, the z, and no 4 forms. Oh, because if you think about it, the form the x wedge the x, this must be alternating, right? And so it must be 0. Okay, this means that on all the possible forms, all the possible, alternating maps, you have a classification by the degree. So the set of all the possible alternating maps, which is of course an algebra, you can make internal multiplication by this wedge. You have a when you have a multilinear map, you can split it into the sum of a 2-linear map, a 3-linear map, a 4-linear map, and so on. Okay, and this is expressed in this way. This is the algebra of all multilinear maps alternating. Okay, and you can split it into this way, an infinite sum, and you can prove that when the of course, this sum stops to n, which is what I was telling you. That if you go over n, then in the wedge product of n plus 1 generators, you will have 1 at least, which is twice. And so that will nullify the product. Okay. And the basis, this is what I was telling you. The basis is given, you see summary. For any basis, the dual basis alpha j generates the K form, the K multilinear maps. Okay. Okay, finally, differential forms. This is what I was talking about. After that, there is a pause. Okay, so yes, small break. Now, remember what was a vector field? A vector field was given an open set U in Rn. For every point of this open set, you have a tangent vector. And I told you it was a tangent vector to Rn, but since P is in this U, this was a map into several tangent spaces with different P. Maybe I didn't tell you, but this can be formalized by making the union. If you take the union with E ranging into the open set, this means that you are taking the set of all tangent spaces. Okay? And to every point, I'm taking one single vector of one of these tangent spaces. This is the point of that picture. These are different points. This is U. For every point of U, I'm taking a vector which is tangent in P. You see the abstraction. I mean, all these vectors are elements of Rn. But you see that they are not really in the same Rn, because this vector is pointed here, this vector is pointed here. In this sense, if you have a vector field giving you this vector, all parallel, all the same length, these are all the same in Rn. But this is not the same. The vector when you use the coordinates, the spatial coordinates of your spatial Rn, they become the same, but they are not the same. And this is expressed by the fact that we can take the union here of all the tangent spaces. And the vector field is just a map in this way. Well, now you know what? I have also the cotangent space, the dual. This is the dual. So these are the map from the tangent space to R. This is a vector space by itself, okay? So now don't think about them as maps, okay? Just think as elements of a vector space, which is called the dual. This helps. Otherwise, you are adding a layer of complication that you don't need at the moment. So don't think of them just like this. They are just vectors. This is a vector space, right? So they are vectors. If you like the idea, think of them as arrows. Okay, not the same arrows as before. But these are just vectors. And as before, I can take for every point in an open set, one of these vectors in one of these cotangent space. You see, I just have to add the two letters co to the previous sentences. And in this way, I obtain not a vector field, but a co-vector field, if you like the terminology, okay? I don't like co-vector field. Could we call it in another way? Maybe differential form. What do you think? You like the word? These are the differential forms in Rn. Maps from an open set, and for each point I will have an element of the dual space of the tangent space in the point. It's more difficult to say than to understand. Okay, and this is the map. And so this is a differential point, the differential form in a point, in the point P, which is just a vector, which is actually a map on tangent vectors. Okay, I can feel the pain in your eyes. Now, let's try this. Let's try this. I have a function from Rn to R. And I want you to produce from this function a differential one form that will be called df. Okay, so I want df equal to something that you will have to tell me, but I tell you what it should be, in what space it is living. This should be, the f should be a differential one form. That is, the F should map, let's say, all Rn, map Rn into the union of the tangent space to Rn dual union over all the points of Rn. And in particular, should map a point P to some df in P. That is in this space here. So at the end, you just have to tell me what is this df of P. Okay, this is what I'm asking you. Can you define df in the point P for every point of Rn? Let's go on. I mean, we just have to cook the only ingredients we have. You can't be wrong. Okay, you have to produce the F in P, which is an element in this space. What is this space? The dual space to a vector space.
Should be a map from Rn to R.
Okay, but please don't say Rn.
Sorry.
But the tangent in the point
exactly.
P. This is very important. I know that this is Rn, okay, but it is not, actually. It is very different. Yes, it is Rn only in this special case, but it is the tangent space, but perfect, a map to R. Would you like to go on? Right. To define a map, I give you an input. So we have a tangent vector in V, and you have only to fill this blank. So this should be you have to put together the ingredient up to now. Okay, what are the ingredients for the moment? What do you have? You are cooking, and I'm presenting you with just 2 ingredients actually. So that should be a very easy recipe. Well, 3 ingredients then. The point, which I already used, I will use again, but I already used to choose the vector in the point. But there is the first ingredient. You are missing the first ingredient. We started from a function, guys. You have to use the function, okay? This is the differential of the function. So the third ingredient is the function. Can you cook up something with these ingredients? Okay, the directional derivative, well, it can work. I mean, this is a tangent vector, which is the directional derivative of functions, and you have a function.
So you can apply P to F.
Exactly. This is the directional derivative of F. And one could say, what does it mean, a tangent vector applied to a function? Well, that was why I was talking about a new way of looking at tangent vectors. Exactly. Okay. Otherwise, you couldn't do this. I mean, otherwise, now I should tell you, take the scalar product of the gradient of the function, something like this. Okay. df is a map. df in a point is an element of this cotangent space. df in a point evaluated on a vector is finally a number. Okay?
Yes.
Differential one form before applying point. So
the differential one form is the one before the point, yes. Because the differential part means, I haven't told you up to now, but means that as a map from U to this union over P in U of cotangent spaces, as a map this way is smooth, is chi infinity. And of course, now you should ask, okay, but what does it mean, smooth as a map in the union over P? Yes, that's a problem. In order to define clearly this, we need to put a structural manifold on this set. And this will be the last chapter, chapter 14. Okay, so for the moment, let's go on and let's check if the definition is correct. Congratulations. This is the definition. Okay. Okay. Now look what happens. What? Oh yes. What is the differential? So now, can you tell me what is the x now? You see, suddenly the x has a meaning. What is the meaning? You just need to understand that x is, you do the differential of what? Differential. You do the differential of a function. So you should tell me if x is a function. Is it? Yes. Yeah. It's called projection on the first coordinate. Yes?
Yes,
Tell me.
Yes. Yes. Yes.
Okay. Okay. Is that clear? I mean, we are used to think to x just as a symbol, but x is a function, y is a function, z is a function. In this way, you can do dx, which is the differential of the function. Okay? And you know what? There is something more that I haven't told you. What is this symbol? D in the x. D in the x is the operation, in abstract way, is the operation that takes a function and gives you the derivative of that function, probably the index in a point, gives you the derivative of that function in that point. So, in other words, D in the x is a tangent vector. In this new way, okay, D in the x is a tangent vector at P. And of course, if you look at the tangent vectors at P to Rn, just like Rn, you forget the point of tangency. This is just the vector 1, 0, 0, 0, 0. Okay, is the derivative in the direction of x. And remember, what was the association with the original idea of vectors? Take the derivative in that direction. Okay, perfect. And in particular, this means that this kind of tangent vectors are a basis for the tangent space. You remember I was telling you there is the dual base. Question. So I just told you the in the x1 in the point. To Rn in that point. What is the dual basis? Just to make you understand that everything is just fits, it just works. What is the dual basis? What do you think would be?
The differential forms, the x1 with the other.
The x1.
Yeah.
The xn, exactly. Of course, in the point P. Okay. Of course, this is a theorem. Okay. You don't need to trust me. You can work it out, but in order to work it out, and that would be a very nice exercise, actually, you need to remember what is this symbol, what does it mean, okay? The meaning of the symbols, where they live, what they do, what they act on, that should be your second, I would say your first nature. Okay, it's the only way you can really understand differential geometry. When you say df, you should ask what is the f? Okay, is a one form, meaning, well, in a point is this, acting on vectors in P and then gives me numbers. This is sort of, I don't know, when you do physics, when you have an equation, first thing I would say, you look at the dimensions. I mean, if I have kilograms and I have joule, there is something wrong. Kilograms are not joule, okay? So that equation doesn't work, there is something wrong. You do the same here. If at a certain point you have an expression which gives you a form, and this is equal to an expression which gives you vectors, there is something wrong. Okay, the same as for physics or other. Okay, so, and I was telling you that this is called differential form because it is C infinity, okay? I was telling you that the notion of C infinity will be given at the end of this lecture when we will have this differentiable structure on this union. But for the moment, you can just think that the differential form for what we are saying is just given in coordinates by functions. In this case, the differential of a function, these are the partial derivatives. But in general, the differential form will be a combination of the standard differential form, the coordinates, the canonical coordinates, differential forms, and these coefficients are functions. Well, we can say that the differential form is smooth, and that it is a differential form, when all these functions are smooth. And this is just nothing more than when you say a function f from R3 to R2 is smooth when the corresponding two functions are smooth. Okay, these are the coordinate functions. Okay, these are differential form. I already told you, just a matter of notation. And the differential, the k differential forms are denoted by this capital omega. So by omega 1, I mean the one differential form. So for instance, for what I told you, the x is in omega 1 of Rn, and so on. Of course, I can do, I mean, differential form are alternating maps, right? So I can do the wedge product as usual. So you now have a meaning to the x wedge the y. And I think, okay, just an example. These are the coordinates on R3. Then the one forms are linear combination of this, right? Wait, linear combination when evaluated in a point. This means that these are functions. Okay, where these are functions, of course, C infinity functions. And that means that two forms are of this way, and three forms are this way. And okay, just this. Well, remember that a tangent vector was acting on gerbs of functions, and then a vector field was acting on functions, giving functions. Now you can combine all of this, and you can say that the differential form, the one differential form, act on vector fields. In this way, I have a one form. I can put inside the one form a vector field, and I want to check what happens. Well, the result is a function on Rn for the moment. Can you see how? Well, evaluate the vector field in a point. This is a tangent vector, right? Evaluate the differential form in the same point. This is a linear map on tangent vectors. Apply this, and you obtain a number. This means that this is a function of a point, giving numbers when applied to points. Can you see that? I mean, the big picture. You don't need to make. These are not formulas that you need to memorize. Otherwise, you're not going anywhere. Just everything is natural. In particular, if you have a two-form or a three-form, a two-form will be fed with two vector fields. So you can do this. Put two vector fields inside, and you obtain a function. You see, so three forms are taking inside, their food is three vector fields, and so on. This is the notion of tensors. Okay, and this is what I was telling. In words, a K form takes K vector fields and returns a function. Okay, the exterior derivative. I told you, yes, this is, I guess, the last point. I told you how to do the differential of a function, right? And I told you also that a one form is the sum of functions times this. Well, I define a new meaning of the differential, not only the differential of one function, but I will give you also the meaning of differential of a one form, which is by definition just the differential of these functions. I can do this because I know what this is, and I have to multiply it times this differential. But the multiplication in the alternating world, in the alternating realm, is the wedge product. Okay? So we have this definition. The differential of a one form is the differential of the coefficients wedge the differential of the basic form. Okay? This is actually a definition for omega k. This is a multi-index, which is a shortcut for dx1 wedge, dx2 wedge, I don't know, dx4. This is corresponding to the multi-index 1, 2, 4. It's just a shortcut to the node higher dimensional differential forms. Okay, this operator is called the exterior derivative. That is a map. The exterior derivative is a map taking K form and returning K plus 1 forms. Okay? A zero form is just a function, if you think. So the differential is taking a zero form, returning a one form. And if you are picky, you should tell me, okay, this is not this is dk, of course. But we denote this by just d. Okay, and this is called the exterior derivative or the differential. Very good, very good, very good. And now, before stopping, you know the fact that on Rn, how it is called, if you take, when you didn't know what was the symbol, right? Well, it happens that if you take again the exterior derivative, you obtain zero. This is a general property of this map. This map is made in such a way that if you take it twice, you obtain zero. Okay, for the moment, just trust this property. Let me check. This is actually the Poincare lemma. You know what it is, the Poincare lemma? No? Okay. Okay, for the moment, just trust me on the fact that this square is equal to 0. Apply from every, I mean, you start from forms of degree 10, you go by differentiating them to forms of degree 11, and then you go again to form of degree 12, then you obtain 0 from whatever degree you start. This square is always 0. Okay? Now, look at this. You know what is the gradient of f? I guess you use it, right? The gradient of f, you agree, is this one, right? So it's just the three partial derivatives. Perfect. You know what it is, the curl? Probably you know better than me. This is more or less the first time I met this term, is this one, okay? And the divergence, this I know actually, is this one. Perfect. Now, look this sentence. Every one form is a linear combination of the x, the y, the z. And so, since this is the dual basis with respect to the in the x, the in the y, the in the z, as a vector space, when you make the identification that the tangent space in a point to R3 is equal to R3, you understand that this identification is the same for the cotangent space. I mean, they are all vector spaces of dimension 3. They are all isomorphic to R3. And in this identification, the x is just corresponding to the partial derivative, because by definition, they are the dual basis. The identification is made just this way. This means that if you have a one form, this one form is just a tangent vector in this identification, okay? And this means, for the same reason, that if you call this the first vector of a basis, this the second vector of a basis, and this the third vector of a basis, then a two form can be identified with the vector. And a three form can be identified with just a function, because there is only one three form. The dimension of the three form as a vector space is just one. So this is just R. And now look, the magic happens. If I take this identification, this tangent vector corresponds to this, but this corresponds to a differential form. In this correspondence, the differential form is just the gradient of f. In this correspondence, the differential of the one form, that is a two form, if you compute the coefficients, they are just this. So this means that in this correspondence, the curve is just the differential. And if you do the same for two forms, in this correspondence, the divergence is just the differential. So gradient, curve, and divergence are just the same thing with respect to this intrinsic point of view, just an expression of the differential. And you probably have this theorem. In analysis, you do this theorem. If you take the curl of the gradient, you obtain 0. You know what? I just told you this is the differential of rank 1, and this is the differential of rank 2. And I also told you that if you compose twice the differential, it becomes 0. You probably know also that the divergence of the curl of the vector is 0. Well, you know what? It's exactly for the same reason. This is the differential rank 2, and this is the differential rank 3. From 1 to 2 and from 2 to 3, actually. And so this is just another expression, the differential square with 0.
But the gradient of a gradient is not 0. So where is
the gradient is taken on function. Dimensionally, you can take the gradient of a gradient. This gives you 3 functions, so you can take only the next step, which is the curl. Well, in this way, you could take the divergence, and so it doesn't work, because in this correspondence, these are different space. But you could describe, anyway, the divergence of a gradient in terms of differential geometry with these operators, okay? And then this third proposition is the Poincare lemma, I guess. Okay. Well, yeah, there are other things, but I think that please we skip this and break. Okay. Now, manifolds, finally. Why finally? Because this is the main object in differential geometry, okay? So I'm now going to define what are these differentiable manifolds and why looking just at Rn is unsatisfactory. Okay, just the intuition is this one. A manifold is a set, okay, that locally looks like, you see quoted, looks like, because what you are now going to do is to formalize in a mathematical way, in a correct formal way, what does it mean looking like an open set in Rn. And by the way, remember at the beginning I told you that all connected open sets in Rn are just Rn by the stereographic projection, more or less. So this means that the manifold is a set that locally looks like just Rn. Okay, so that means in particular, once we have formalized what we mean by locally looking like, it means that every construction that we have made on Rn will be possible to repeat that construction locally. Okay, so first of all, we have to define a differentiable structure. We have to define what it is, something which is that you can take derivatives infinite times. Do you agree, at least qualitatively, that we should start with the notion of continuity? So we should say what is the minimum we require in order to have continuous function and so on. After that, we will look to the fact that you want also taking derivatives, okay? So what we are starting with is the notion of topological manifolds, which is very much less than differentiable manifolds, okay? But it is anyway manifold. Manifold means locally looks like, okay? And the first word tells you to what the manifold locally looks like. A topological manifold locally looks like a topological space. Okay, well, not a topological space, but always Rn. I mean, it's the notion of looking like that is only topological and not differentiable. Okay, a topological space. You see, there is a question mark. Do you know what is a topological space? This I do not expect the answer is yes. Is yes. I mean, do you know what is a topological space? But
no, I'm sorry, I don't know. No.
Okay, so just very quick, a topological space, is a space where you have open sets. You're saying probably, okay, this is not very helpful. Do you know the notion of continuous function? Yes, I guess. A function is continuous if for every epsilon there is a delta, blah, 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 right? That was the definition. Okay. In more advanced terms, a function is continuous if for every neighborhood of the point of arrival, there is a neighborhood of the starting point such that, okay, a neighborhood, I told you just in the very beginning of this lecture, you probably call neighborhood the circular neighborhood. That is in R square, a neighborhood of this point centered in this point is the circular disk, the disk or radius something, and center the point. Well, actually, a neighborhood is any open set containing the point, and a function is continuous if for every open set in the rival space, in a function f from x to y, is continuous if for every open set in y, f minus 1 for every open set A in y, f minus 1 A is open in x. Okay, this is the general notion of continuous function, which is exactly this in terms of epsilon and delta and circular neighborhoods. But what I want to point out is that the important notion is the one of open sets. So a topological space is just any set in which you know what are the open sets. So you need to have a family, let's call it A. Well, I'm using A for aperto in Italian, sorry. You have a family A contained in the subset of X. And this is, of course, satisfying certain axioms, certain properties that I will not tell you. Okay, but properties that makes that a family of open sets. For instance, you know that the union of two open sets is open, right? This is an axiom from this axiomatic point of view. And actually, the infinite union of open sets is still open. This is a property of this open sets family. And so on. Okay, so a topological space is a space where you can talk about continuous functions. Okay, so first of all, a manifold is a topological space. Okay, that's really the minimum. We want to take functions which are differentiable infinite times. At least we should be able to take functions which are continuous. Now we want this space locally looks like the Euclidean space. Euclidean of dimension n means just Rn. And locally looks like means just the following. For every point into this space, let's call, since this will be a manifold, let's call this M as manifold. For every point in M, there is an open set. Open set, how it is called here? U, of course. There is an open set U in X. And what does it mean that locally looks like? It means that this open set, it is like Rn. what do you think it means? It is like. What does it mean that homeomorphic? You know this word? Yes, perfect. It looks like means that such that there is a map, let's say phi, right, from U to Rn, which is bijective, of course, looking like at least there must be a one-to-one correspondence, continuous, and since it is bijective, there is an inverse. Also, the inverse is continuous. All of this is what is called to be an homeomorphism. Homeomorphism from U to Rn. Okay, and you understand that this means locally looks like, this means that U is from every point of view just Rn. Well, from every point of view, for what concerns properties related to continuous functions, to the property of being continuous. Of course, there is nothing here that gives the differentiability. It's not even defined what it is to be differentiable. Okay? So, up to now, is this clear? This space is called locally Euclidean. So, locally Euclidean means that locally looks like Rn in the topological sense. That means topological notion is encoded here in this word. Homeomorphism means continuous and inverse continuous. Now, this pair is called a chart because it is a chart just like in maps. I mean, in geography, you have maps. If you think about it, you have a flat piece of paper telling you how the Earth is made. The Earth is a sphere, okay? It's not a piece of paper. But if you look around the city where you live, in the map, you will find that locally the Earth looks like that piece of paper, which is R squared. We are saying that the Earth, okay, this word is a two-dimensional manifold that locally looks like a part, an open set of this map, and this is why this is called the chart. The map is not bijective. What do you mean? Oh yes, there are several. Yes, yes. Every point in M has a neighborhood, as a U. For every point, you can find a chart. Of course, it's not unique. And of course, this is the difference from Rn. You know what? In Rn, you have just one chart. I mean, you can find a big chart covering all Rn. Try doing this on the sphere. You can't, because there is no way the sphere by itself is homeomorphic to Rn. Okay? This is exactly the problem. Now, the rest of this part of the definition is just saying that this topological manifold, in order to be a manifold, should be not only locally Euclidean, but also should not be a horrible topological space. Topological spaces can be really ugly, trust me. You can build what are called pathological examples. La pulce e il pettine. There is an example called this way. That they are topological spaces, very, very bad. Okay, the minimum you ask to a topological space in order for all we are going to say to make sense is that this topological space is Hausdorff and second countable. Just to tell you what can happen in a topological space, I will tell you what does it mean Hausdorff. And this, of course, means also that there are spaces which are not Hausdorff. Hausdorff means this. These are not eyes. These are just 2 points. Hausdorff means that whatever 2 points distinct you take, you can always find an open set around this and an open set around this that are separating these 2 points. Come on, can you think about a space which doesn't satisfy this property? Of course, I mean, the points must be distinct. As soon as they are distinct, in your mind, they are separable by open sets. Well, for certain spaces, this is not possible. You want to look which one, for instance, should be here. Okay, no, it's not. But I can tell you. This space, take the segment, take this point, remove it, and put 2 points. And now declare that open sets are, of course, all open sets on the rest. But now the problem is, what are the open sets containing this point? Well, what would you expect? This part together with this point. And what are open sets containing this point? The same containing this point, but not this. Can you separate these 2 points? No way. This is not Hausdorff. Okay, just to give you the taste what can happen in topology. Okay, this is very interesting. These examples, I mean, they are, I say ugly, but not in the expression in that sense. And I mean, they are very interesting. But we are not concerned with this kind of spaces because a topological manifold is Hausdorff. And second countable means that you can have a family of open sets covering your manifold, which is countable. You know what does it mean countable, right? And for instance, Rn, is this space second countable? This is a tricky question. Why not? Because if you take the open sets, they are not countable. Yes, I didn't say that all the open sets must be countable. I said you can cover the space, you can find the basis of the topology of open sets, which is countable. You can take balls, not yet countable, because if you take balls with every center, but you can take center which are rational coordinates. Do you know that rational numbers are countable, right? Okay, just take the centers that are rational and the radius which is rational. In this way, you obtain a huge but countable family of open sets which is covering, approximating every point into your space. So Rn is second countable. Otherwise, we would have a problem. Okay. Yes, yes. These are the definition here. Oh yes, it happens. You mean that is not satisfied?
Yeah.
Yes, yes, of course. Of course, all these notions exist. I mean, there are Daniel is saying that there are situations, very interesting, very important situation, when the resulting space is naturally not an Hausdorff space, does not satisfy this. Okay, first example of topological manifold, the Euclidean space itself. I told you this is Hausdorff, this is second countable. And can you find charts covering every point? Yes. There is just one single chart. What does it mean, this symbol? That the open set is Rn. And what is this? The identity maps. Remember, a chart is the open set and the map mapping the open set to Rn. In this case, the open set is Rn by itself, and we are saying that the map is the identity. Is this map continuous? Well, is the inverse continuous? Yes, okay. You have verified your first example of topological manifold. This is the prime example of a topological manifold. And of course, for the same reason, every open subset is also a topological manifold with the same chart, more or less. Okay. Other examples, for instance, this cross is a topological manifold. Of course, the troubling point is the intersection. Can you find a neighborhood of this point which locally looks like an open set of R? No. Can you prove it? I mean, you are saying that there are no open set homeomorphic to this one. I mean, this is an open set with just one connected component. Why shouldn't it be possible to build a map, maybe a very complicated map that you can't see right now, but an homeomorphism with the interval, with an interval? Is this homeomorphic? Well, the answer is no, but just to understand that this is not trivial. I mean, you need properties of continuous maps. Do you want to say something?
The projection and the point of intersection.
How can you say? I mean, it's not evident because you are thinking that this is just two intervals overlapping, but I mean, there can be a map. I mean, a disk is homeomorphic to Rn. This is very counterintuitive, no? I mean, well, there is a way to prove this. Remove this point. If there is a homeomorphism, this would remain a homeomorphism with the interval with the point removed, right? Which point? The image of this point, I mean. And now, how many components has this space? 4. How many components has an interval with a point removed? 2. Well, theorem, a continuous map preserves connected components. Sorry, not a continuous map, a homeomorphism preserves the connected components. There can't be an homeomorphism sending 4 connected components into 2. Okay, so you need, I mean, it's not trivial. Also, this theorem, you have to prove it. Okay, so topology, also very easy statements like this are not trivial usually. Okay, now let's go to the notion of C infinity. And just look at this picture. Everything looks like Rn. So now you want to define what does it mean for...
Excuse me.
Yes?
We can see the current screen now. I see the topological manifold is Hausdorff for second countable. So few pages.
Some of you.
The screen is stuck for me as well.
Okay, for you it's stuck. I'm moving now.
For me too. Yeah, also for me.
Okay, let me check. I'm tethering, so let me check. I can try to speak more. Okay, but you can hear me, right? 1, 2, 3. Can you hear
Yes, we
me?
can hear you, but cannot see the shared screen.
Okay, I will stop the sharing and I will reshare. Okay, sharing is stopped. I do it again. Okay, I'm sharing again. Is now working?
Yes. Yes.
Okay, perfect. Thank you very much. So now very, very important. We want to introduce the notion of differentiable manifold. So in some sense, we should put inside the definition of topological manifold the differentiability, okay? And we already know that our manifold is locally like Rn. So it means that around the point, this is Rn. This is Rn means that there is this map to Rn. And also this one, it is locally like Rn. This means there is this map going to Rn. Now, we ask for the following. On the intersection of two of these charts, whenever they intersect, of course, there are a lot of charts that are not intersecting with each other, okay? But if they intersect, we ask, and this is the big step making everything else working. The domain of the chart. Okay, I'm calling chart U phi, the pair U phi. This is the chart. And when I say, we say abuso di linguaggio in mathematical language, it means I should say, if the chart is the map, I should say when the domain of two charts intersects. But usually I say chart to mean the map or the set. No, good point, good point. So when the two open sets intersect in this way, you understand that you have a map here into the corresponding subset of Rn here, and you have a map here into the corresponding subsets, okay? And you can compose this map, the inverse of this map, -1, you can compose with psi. Okay, this map composed this way and the other map composed this way, these are called the transition function. The transition from here to here. The transition from one Rn to the other Rn. The maps that will change the basis. The maps that will make the basis not canonical. When you're locally looking at things here, you have a canonical base. That means the usual canonical base of Rn. But when you are looking here, you have another basis. And sometimes here and here can coexist. This is the point. In the same time, you can have two different Rn. And if you define something in Rn, this should be coherent with these two representations. I mean, if you define something that is the same here and here, but this is not defining an object here, because this map probably is not the identity. Okay, so the object you are defining should change according to this transition function. Exactly. The coordinates should change according to a certain transformation rule, which is exactly the language you learned for tensors in Rn. A tensor is a rule giving these indexes where the indexes change in this way. It means exactly this. That tensor is just a very nice object on the whole manifold. But when you look at the tensor locally in the charts, if you are looking just a special part of that object. This is the problem. Then, in order to introduce the differentiability in the topological manifold, we just ask that these maps are to infinity. So we ask that these maps are C infinity on the domain. This map is C infinity here on U intersected U, V, and so on. This map is C infinity here. Does it make sense, C infinity? Yes, these are subsets of Rn, okay? This is the point. Everything is in Rn. So you know what does it mean, C infinity. Okay, so I will say that two charts are compatible if their transitions are C infinity. Okay, now take a locally Euclidean space and assume that the charts are pairwise C infinity compatible. And you obtain a differentiable manifold. So from now on, a differentiable manifold is something where you have a picture like this. Let me remove some garbage. You have a picture like this, okay? And moreover, you know that when you go from here to here, this map is C infinity. For whatever chart you take two charts. If they intersect in the way I'm saying, then the composition, the transition function, this one, is C infinity. By definition, okay? This is a differentiable manifold. And this is what it means locally looks like Rn. Question. Is the unit circle a manifold? Can we try to check if it is a manifold just with a picture? Answer, of course, is yes. What do we need to do in order to prove that it is a manifold? We need to find the chart or a system of charts that are locally like, of course, it's a manifold of dimension 1, locally looks like R. Would you say that this circle, this line locally looks like an open interval? Yes, we just need to formalize this. Okay, and for instance, I can take just two charts. Take U2. This chart is a chart that does not contain this point. So this point can you see that they overlap in almost all S1? They overlap on the union of these two connected components, A union B. Well, you have to prove, you have to compute that on the overlapping set, on A union B, the transition function is smooth. And of course, I have to define this is U, sorry. Okay, this is U. I need also phi. Okay, I need phi 2. And in this example, you have U1. And of course, if you want to define the things, you need a representation of the unit circle. I can't just say this is a unit circle. In this case, the unit circle is represented as a set of points in the complex plane in this way. That means with a theta, an angle. Okay, and in this way you have a representation. These are the open sets in the picture, and I define these two maps. Well, these two maps are, of course, what you would expect, just sending in the angle. But this angle is going with this argument. These are just branches of the logarithm in the complex plane. And in this way, if you compute the transitions, you obtain this. Okay, it's not evident, and I strongly invite you to do this exercise. Now we don't have time, but I invite you to do it to understand what happens. But when you do this, at the end you will say, okay, this map is C infinity. This map is C infinity. So these two charts are compatible, and so by definition, these two charts make an atlas. This is the terminology for the set of all the charts. Make an atlas such that S1 is a differentiable manifold. Okay. Okay. Skip a lot of things. Smooth manifold, essentially, I told you, I will skip the maximal atlas part. Now, there is a technical problem. And on the circle, I have given you two charts, but sometimes you need another one. And you can show that the third one is compatible with the two charts. Well, so the differentiable manifold is not only S1 with an atlas, with two charts, is S1 with all the possible charts which are compatible with that two. Okay, so if you can find a new chart which is compatible in the differentiable meaning with the original two ones, put inside the atlas. In this way, we can use any chart we like on S1. Because sometimes you need a certain chart which is very small or bigger and so on. Okay? And this is called the maximal atlas. It's just a technicality. After that, every theorem we do, the theorem will say this property is true if and only if is true on the maximal atlas, if and only if it's true on one single atlas of your choice. So usually you just prove the property on the atlas you prefer. Okay. Examples. We already said that every Rn is a manifold. Now we are saying it is a smooth manifold. And there are manifolds of dimension 0 that locally looks like R to 0. What is R to 0? Just a point. So what are manifolds of dimension 0? Manifolds such that every point is an open set, because R0, the single point is open. Now, topological spaces where every single point is open are called discrete spaces. And since your topological manifolds are second countable, this means that the manifold of dimension 0 is just a countable discrete space. Okay, we will never be interested in manifolds of dimension 0, but just to know what it is. The graph of the smooth function. Look, this graph, whatever the function is a manifold. Of course, the function must be differentiable, must be smooth. What is the chart? The chart is the projection. You see? Since this is a function, it means that there are no self-intersection going back, and so the projection is at least bijective, and you can prove that the fact that the map is smooth means that this projection is smooth. And also the inverse is smooth, okay? And you can show that these kind of charts are related and so on. Okay, other examples. Yes, manifolds of dimension 1 are but yes, I'm not sure it's so clear why you can only attach this way. Yeah. Okay, I repeat for the streaming. And okay, so we are saying that the manifolds of dimension 1 are very easy to remember. Differentiable manifold of the dimension 1 or topological manifolds of dimension 1 are just the real line, all are, if they are not bounded in some way, if they are not compact sets, or when they are compact, they must be just S1. The reason is my opinion, is not really trivial, is the fact that when you have the overlapping of two open sets, the fact is that the open sets on the reals are just intervals, and there is essentially only one way you can have this map on the intersection of two overlapping intervals. Okay, well, we can say also surfaces then. Yes, if you try to do the same, to classify surfaces, that is differentiable manifold of dimension 2, first, I don't know for the non-compact case, but if you ask for compactness, that manifold is closed and bounded, okay? And then you obtain a very nice classification. That is, you obtain the sphere, you obtain the torus. You know what it's the torus is the salvagente. And the torus is you can think is a sphere, but you have made a hole inside. Well, you can think of a torus with two holes. It's not more called the torus, okay? And the number of holes is called the genus of the surface, and compact surfaces are all this way. It's the orientable ones, yes, okay. There is an additional condition to put. Okay, as you can see, just switching from dimension 1 to dimension 2, things becomes more difficult, okay? Anyway, we are not interested in classification for the moment, okay? So we are just giving examples, sparse examples, and we are in particular trying to give ways of building new examples from previous ones. For instance, if I have two manifolds, I can take the Cartesian product of the two manifolds. Natural question, is this yet still a manifold? Yes, it is. It is called the product manifold. Of course, you have to define the charts. Of course, you have to define the open sets, the local coordinates, and so on. There is no point in what I'm saying. There is no part that I'm saying that is trivial. Okay, everything I'm saying would require a proof, and you can find the proof in the book. Remember, aim of these lectures is you become able to read this book, not you learn all the differential geometry in 4 hours or in 20 hours. Okay. And this is the torus. This is a non-compact two-dimensional manifold, which is the cylinder, right? And okay. Yes. No, okay, this is a problem that I invite you to do with the hint. Okay, this is the smooth Poincare conjecture. We can skip it. What's the time now? Okay, yes. So we go on. So second ingredient that we need is what are smooth maps on a manifold. Remember, we are doing this. We need the differentiable manifolds in order to do the equivalent of analysis on Rn. On Rn, we do analysis on functions. We take derivatives of functions, okay? So how can we take the derivative of a function on a manifold? But first things first, what is a smooth? What is a map which you can take the derivative? What is a smooth function on a manifold? Well, now everything is very easy, always the same. A manifold locally looks like Rn. A function on a manifold is smooth if locally that function is smooth. What does it mean, look? Means take a microscope, take a magnifying glass, it's called, look around P with this magnifying glass. This is a chart. It means that locally here, this is just this. This means that your function from M to R is actually a function from here to R. Formally, it's just F composed with the map giving you the local coordinates, okay? But I invite you, when you're doing proofs, then you need this. But now you're just understanding what does it mean. Your manifold locally is Rn. So this means that your map locally is a map from Rn to R. And we will say it is smooth, the original map, when this map is smooth. Okay? This is just the point for whatever we are now going to do. Now there is a question, and every time you do something like this, there will be a question, and the answer will be always yes. The question is, but wait a moment, I can have another chart. I can have another map, another U with another map which is C of the same, not the same, but of another chart which is still containing point P. Can happen that this map is smooth, but this map is not smooth. If this could happen, this would be a problem. We would say that our definition of smoothness is not well posed, it's not well defined, no? Because you must find the right chart. Well, this cannot happen. And you know why this cannot happen? Because when you go from one chart to the other chart, that map is smooth. And so if this is smooth, then also composed with this one is smooth. By definition, exactly. But if you want to prove it, you need to do such a picture and to prove it. This is a theorem. Okay? And now, what I was telling you, a theorem like this, we will have several. The function is smooth, is the same as the manifold has one atlas such that locally for this atlas, the map is smooth. And for the maximal atlas, that means for every chart you can find on the manifold, your map, this function, is smooth. These are all equivalent. And usually we use this. We just choose a single atlas and we prove this. Okay. Now, another important notion in differential geometry, I will scatter through pages now because I told you now everything is more or less just the same we did before. If you have a map from two differentiable manifolds, and then you have a function here on N, so you go here on R, can you build from this map, from this function, sorry, a function on N that is a map from N to R? Yes, of course. Just take the composition. And you're saying, oh, okay, what are you telling us? Well, nothing particular. Well, this is a very general construction. We have a map. We will do this whenever we can. You have something here, in this case a function on this manifold, and we would like the same something, meaning an object of the same type here. In this case, we would like a function here. We say we are pulling back what we have here, we are pulling back it to here, because this was here, and we are pulling it back by using this function. So this simple notion of composing this function is actually, from this point of view, is called the pullback, and you usually use this symbol of H. Think about a general construction that you try to do whenever you can. That is, you have an object, in this case a function, so the pullback is just a composition. But we will have differential forms. We will pull back differential form. We have a differential form here. We will obtain a differential form here. Okay? Whenever you can, you try pulling back objects. And of course, whenever you can, you try pushing forward objects. This is less common, I mean, that you can push forward something. You can push forward tangent vectors, for instance. We will see. Yes?
I don't know, before with the name pushing back, I'm expecting to provide something in M, and then there is something in N, while H composed F seems to be that goes from N.
Pulling, not pushing, sorry, pulling back. Back with respect to this arrow. So you have something here, and you pull back here. I mean, you have a question with the terminology. Okay, so you can tell me later. But I mean, this is over there. This is the arrow, and I'm pulling back to me. So here there is M, and I'm pulling back to N. But anyway, just the terminology, I mean. Okay. For the moment, I told you what are smooth functions, that is maps from M to R. But now I will tell you what are smooth maps from two differentiable manifolds. You know what? As usual, this is a map from two manifolds, right? But this manifold locally looks like Rn. This map will be called smooth when as a map from Rn to Rm is smooth. Nothing more. And this definition is well posed. It's a good definition. It works. Okay? And this is the same as before. The map is infinity. There are atlases for the domain and the codomain of the maps such that the map is smooth, or for every chart, for the maximal atlas on the domain and on the codomain, the map is smooth. Well, so you have a notion of smooth maps between manifolds, right? Question: if you compose two smooth maps between manifolds, is the composition smooth? Well, why are you asking? Of course it is. Why? Because locally everything looks like Rn. Is the composition of smooth maps between Rn and Rm and Rs smooth? Yes, it is. So it is also in this case. And when a map is smooth and it is also a bijection and also the inverse is smooth, then we will say that map is a diffeomorphism. Diffeo means differentiable, and just like homeomorphism means a continuous map with the inverse, and the inverse also continuous. This is, by this word is the general notion of isomorphism. Okay, this is the isomorphism in the category of C-infinity manifolds, if you think about it. Two manifolds which are diffeomorphic, from every point of view we are interested in, are just the same. And what I was telling you at the beginning of this lecture is that the open interval is diffeomorphic to R. Okay, and now you have you know what this means. Okay, and you know, if you want to check for a function from Rn to Rm if it is smooth, how do? You write it as m real functions, right? And you check if all of these are smooth. Well, you can do the same with this notion of smoothness between manifolds. If you have a map from two manifolds, then you can check on every chart if the map with values in Rm, because M is locally like Rm, you can check on the components if they are smooth, and then the map is smooth, and so on. Exercise, we will skip. Examples. Here there is a lot of interesting things, but running out of time, so okay. Partial derivatives. You know how to do partial derivatives, right? These are derivatives in the direction of x, in the direction of the coordinates. And you know that you have coordinates in the manifolds, local coordinates. Okay, I use this term. Local coordinates around P means choose one chart around P. And these are the local coordinates. You are choosing how is the Rn that locally your manifold looks like. Okay, once you have chosen this, so once you have chosen the chart, then you have the partial derivatives. These are just the partial derivatives of your function composed with the chart. As usual, I invite you to think, this is for the formal proof and to understand and to make formal arguments. But just think, my manifold locally is like Rn, and on Rn I can do partial derivatives. So locally, that means choose coordinates, I can do partial derivatives. Okay. And if you have a map between two manifolds, let's say this is a manifold of dimension n, this is a manifold of dimension m, what you can do locally? Locally, this is Rn, and locally, this is Rm, right? So you can do the partial derivatives of this map with respect to these coordinates, with respect to this component. So you can make what is called the Jacobian matrix. So locally, on differentiable manifold, you have also a notion of Jacobian matrix. But remember, all these things depends on the charts you have chosen. Okay. Function theorem we skip. I want to define tangent vectors. That is, no, we skip. Chapter 7 is the best. I like it, but it's more. Yes, because it's topology and this kind of things. Here there is probably the example of a non-Hausdorff space.
Is it difficult to be understood?
No, I don't think so. This is important. Please do it. This is a very important family of example. What's the time? No? Okay, so I will skip. Maybe if we have time, we can get back to this. This is a manifold called the projective space, and it appears in several situations. It is an example of differentiable manifolds that you should keep in mind. Okay, but we need some time to build it. So we will skip this, because I want to get to the tangent space. We need to define tangent vectors, okay? Now we have, you see, this is all on projective space and okay, tangent space. You see, for the moment, we have the notion of differentiable manifold. We have the notion of differentiable maps between manifolds, okay? And now we try to give the notion of tangent vector. If you think about this, I should say, okay, a tangent vector, since your manifold locally looks like Rn, a tangent vector is an arrow in Rn. This doesn't work. I mean, this tangent vector is just on that chart. Okay, so and if you have another chart, I mean, this wouldn't give to you a notion of tangent vector in whatever point. It would be a notion depending on the chart. So we are trying to give an intrinsic definition of tangent vectors. So we have two definitions of tangent vector for the moment. An arrow, that means also column vector, and as a point derivation. What is a point derivation? Let's have a look at this definition. A point derivation is a map, you remember, a vector does the directional derivatives. That means maps smooth function that was in Rn, germs of smooth functions to R, right? Now ask yourself, if I just remove this and I put just the manifold, does this definition make sense? I mean, are all things here well defined? What is the germ of a function at point P into a manifold? Well, exactly like before. It's the equivalence class of functions which are the same around P. This makes sense on the manifold. No charts involved. So if you accept, and you have actually, because we spent 2 hours looking at tangent vectors just as derivations, point derivations. If you accept this, now then it's clear. What is a tangent vector to a manifold in a point P? Is just a derivation of the germs of functions at that point. Okay? Is there a question? I heard some microphone switching on. Okay. So we have the tangent space at the point is just the set of point derivations in that point. It is exactly the same as we did in Rn. Okay. Of course, we have to define what are point derivation and so on. We already defined it on Rm, but they just replace Rm with n. And so, definition: a tangent vector is just a derivation at P. You see how things are simple now. And
Excuse
now,
me.
when you will have it, yes.
Sorry for interrupting. I have a question. When we defined the germ C infinity P for Rn, we said that this is the equivalence class of functions which are the same in that point. But now on a manifold, what is the concept of the same? How we compare two functions on a manifold? Well,
a function is taking values in R. So the two functions are the same if the values
in R is
images are. I mean, okay. You don't need the domain to check if a function is the same. You need the codomain.
Okay, I see.
Am I clear, or
yes,
I didn't get the question?
It's clear. Okay, so it's the same if they go to the same value in R. Okay, that's
exactly.
Thank you.
Just for locally around P, okay? They don't need to be the same for every point in the manifold, just around the point P.
Okay, thank you.
Okay. Well, you know what? If you take all these derivations, you obtain a vector space. Call this vector space TPM. And you see now there is no reference to coordinates. We don't have coordinates. So we can't use coordinates now because we don't have them. If you want coordinates, you have to choose a chart. Why this wasn't happening in Rn? Because in Rn, you always choose a chart from the beginning, which is Rn itself. Okay? And so if you choose a chart, you have tangent vectors only locally defined. So on a manifold, you still can do partial derivatives, but only locally. These partial derivatives are defined around P and requires a choice of U phi. Otherwise, you don't have these local coordinates and you can't do partial derivatives. Okay? Well, and now, if you have a map from N to M, a differentiable maps, you can do the differential of this map, also denoted by F star this way. This map, let's say in a point P, this is a map pushing forward tangent vectors. I told you that you can push forward tangent vectors. So it's a map from here to here, sorry, not in P, but in F of P. How this map is defined? Well, as usual, just put together all the ingredients you have. You have F star, you take a tangent vector, that means you take a tangent vector in P, and you must obtain a tangent vector here. That means you have to apply this to a function, because tangent vectors are derivations on functions, on terms of functions, of course. And if you put together these things, you have just as we did in Rn. This composed with the function. So you have a function of M composed with F, and you obtain a function on N. This is the fullback. In some sense, the differential of x p is xp of the pullback, let's say of f, if the pullback of this. Okay, in some sense, you see these two operations are, in some sense, adjoined with each other, dual with each other. Okay. Okay, the standard properties of these objects that we are defining in such a rush are that they can be composed. If you have a map this way and the map this way, you can make the composition of these two maps going from N to P. And then you ask what happens if you take the differential of this composition this way. But one differential is going this way, the other differential is going this way. It's very natural to check, to ask whether this composition is just the composition of the two maps, and it is actually. This is the derivative of the composition of a function. If you remember, you have f times G. The derivative is just the derivative of f in composed with G, and then times the derivative of G. Okay, this composed with G means that I'm taking the tangent space, is this composition here. Okay, anyway, the chain rule holds. Let me check. Okay, remember the differential of a function is locally given by function times the partial derivatives. This is still true here. This is the general case of a function from Rn to Rm. So we have actually partial derivatives here and partial derivatives here. Okay, so you have this kind of expression. But this is, all of this is just to say that locally you have the same as before. You have a function from two manifolds. Locally you have a Jacobian, for instance, a Jacobian matrix, but only when you fix coordinates, you choose coordinates. Okay. Now, this is a new point of view for tangent vectors that you need to know. For the moment, you know a tangent vector in Rn is an arrow, is a column vector. This doesn't work well for manifolds, so we have chosen a third description, which is the description as a derivation at a point. That means a derivation on the germs of functions at a point. Just think about derivations on function. Okay, now there is a new point of view. That is, you know that when you have a tangent vector, you can find the curve such that passing to the point you are interested in, and the tangent vector to the curve is just that tangent vector. You are integrating the tangent vector, not the tangent vector, but the vector field generating that tangent vector in that point. Anyway, for these reasons, it is important to be able to think about tangent vectors like curves. Okay, so what does it mean, a curve? A curve means a special map from R, or from an open set, into a manifold. Okay, so as a map, you have the differential. So you can take C star. C star, what is doing? Well, let's say C star at the point T0. T naught in, this is a point in R. So this map will go from the tangent space to R this way. I know this is just R, okay, but this map is going from the tangent space. I mean, this is a different R, just like the tangent space to Rn, okay, was different from Rn, and this is going to the tangent space into C of T0 of M, which is now something that we know what it is. We have a definition, okay? So this means that if you choose a tangent vector here, you obtain a tangent vector here. But since this is R, there is a special vector field. There is a special tangent vector here. What is the tangent vector corresponding to 1 in the canonical basis. That is what is called the D in the T, computed in T0. In this new point of view, the tangent vectors are derivations, okay? So just take this tangent vector, apply C star, and you obtain a new tangent vector. So just do this, and you obtain a new tangent vector in the manifold, okay? Call this new tangent vector with this symbol, just like the derivative, okay? So now the symbol C prime in T0 means a tangent vector to the curve, of course, to the original curve represented by C, into the manifold. Can you see what we are doing? Just this is the manifold. Sorry, I need to take the pen. Okay. One moment. Okay, this should be. This is the curve C of T, and you are choosing a point which is the image of T0, and C prime of T0 is just this tangent vector. You say, but it's not an arrow. Yes, it's a derivation, because tangent vectors, now I'm using arrows to give you the idea, but is the derivation corresponding to that arrow? On the manifold, yes, because C is mapping numbers into the manifold. So this is into M, into the manifold. And you see this M is not Rn. Locally, around here, you can look at this as Rn, and then, of course, this will be Rn, and this will be a usual curve. And this C prime will be the usual derivative you do of the curve. I mean, everything works well, but you have to prove. Okay. In particular, here there is a theorem telling you to prove the relation between this notion of tangent vector and the usual derivative of a function. That this happens when you have C from R to R. Now you have two symbols, C prime of T0. I mean, you have the same symbol meaning two different things. This is an element of the tangent space in CT0 of R, but this is also a number. I mean, the derivative of a map from R to R. In order for this to make sense, these two quantities should be related. And, well, it's just that this number is the coefficient of this tangent vector with respect to the standard basis. That means that this is just the derivative times the operation of partial derivatives in the direction of t. Okay, to avoid confusion, here we are just saying that this number is denoted by C point, T0. Okay, so with this symbol, we always mean the tangent vector. Okay. Okay. Now, something happens that we need. Every smooth curve in a manifold gives rise to a tangent vector. This is what we are saying, okay? But if you understand how we argument, our interpretation things, now you should ask something. Is the inverse true? I mean, given every tangent vector in a point, can I find a curve passing through that point such that the tangent vector of the curve at that point is that tangent vector? Yes, it is. This means that I can define tangent vectors in a new way as curves. Of course, I should put an equivalence relation such that the two equivalent curves gives the same tangent vector, okay? And this is a notion which is called the one jet. Okay, this is, but we don't need this term. We just need the fact that when you are thinking about tangent vectors, sometimes it's very useful to think to the curve which is generating that tangent vector. Okay. This never happened when I was preparing the book. Okay, I think we can skip this and we can go to the tangent bundle. Okay, now there is a very big part that I'm skipping. I invite you to read it, which is a part regarding what happens when you have a subset in a manifold. Okay, just a subset, and you ask when is this subset a manifold by itself, and more, when is this subset a manifold with a topology induced by the ambient space, which is a subtle question, and this is the notion of immersion or immersions and embedding, of course, I'm talking about. And okay, this is a different thing, but we are moving also. Okay, the part I was telling now is this this part, and we are now skipping to page 129, which is, I guess, plus 37, 66. And okay, this is the last important piece, the piece that you could have some problem in understanding by yourself. The tangent bundle. Bundle is a word meaning that we are putting together different things in a single set. Okay, and you guess what are these different things? Are the tangent spaces. Remember, in the beginning, we were using very often this kind of set. The union of the tangent space to Rn, it was, now it is to a manifold, with the point ranging in the manifold. In this way, this is just a disjoint union. Okay, in fact, sometimes it is we use this symbol, meaning we are taking the union of different sets. Of course, it is disjoint. I mean, these sets are completely different. They do not live in a single big space. Okay. Well, you remember that a vector field is a map from U or from okay, from Rn into the union for P into Rn of the tangent space to Rn. Okay, and I told you this vector field is smooth if its components in the other way is smooth and so on. We would like this vector field to be smooth as a map from Rn to this. We would like the notion of a vector field on a differentiable manifold as being smooth when it is smooth as a map in this way. What do you need in order for this to work? I mean, to be able to speak about smoothness of this map, you need this to be a differentiable manifold. This is, of course, and you need this to be a differentiable manifold. But this is, for the moment, just this union of sets. So you need this to be a differentiable manifold. This is the topic of this chapter, of this section, the last part of this lecture. Okay, and we have a plan for giving this a structure of manifold. The plan is this. Well, first define the set, and we already did this. This is the set that must become a manifold. Before being a manifold, you need to make this set a topological space, right? And then this topological space should look like Rn. We are turning it into a manifold. Actually, this is making it a topological manifold, and point 4 is make it a smooth manifold. Prove that the atlas we have chosen to make it a topological manifold is actually a smooth atlas. That is, on the intersections, the transitions are smooth. Okay. Well, I try to explain with a picture instead of going through. Now we have a manifold. This is the manifold N. And I have in every point a tangent space. For every point I have, you can think about a line on this point. Okay? Why a line? Because it is a vector space. Vector spaces are linear objects. Okay, if the of course a line is a vector space of dimension 1, but if it is a vector space of dimension 2, think about a line of dimension 2. It's called a plane, but I'm not able to draw a plane over every point. And also, if the plane is dimension 7, then we are in trouble. Okay, so we just think about lines, meaning they are vector spaces over the point. Okay. Now, I want to give a topology to all these vector spaces over the manifold, which is including also the manifold. In some sense, the manifold is the base of this space. Over each point of the manifold, there is this line. Okay. Now, the topology is something that needs open sets. Well, you can define open sets locally, actually. I mean, you can define what is called the fundamental system of neighborhoods. That means for every point, you can define a basis of neighborhoods that is generating all the topology. Okay, so this is a good news, actually, because this means that we can work locally in order to define the topology. Okay, so go locally, go local. Let's go local. This is a local set. So now we are just looking here. I will remove all the fibers here. I go local on U. And now I take only this point. Okay, this is a chart. So this means this is not U. This is, I mean, this is U, but I prefer to call it Rn. Okay, I don't know why it's not working. This. Okay, it's working with a delay. So this is locally, this is Rn. Okay, and we know that in Rn, every vector is given by as coordinates with respect to these coordinates. So this vector v is actually a vector, is actually v1, vn, okay, with respect to the partial derivatives in the directions given by these coordinates, but I'm in these coordinates, okay? So this means that this union for points in the local charts of the tangent space to your manifold in this point. Now, the tangent space to your manifold in this point is just the tangent space to Rn, because we are looking locally to Rn. So this is just Rn. And so this union at the end is just U times Rn. I mean, now that you are local, a tangent vector is just a point and the coordinates of the tangent vector at that point. Okay, so a tangent vector is this point and the vector v1, vn. Usually this is the tangent vector in Rn, okay, in the very old definition. Well, this means that I mean, this U is an open set in Rn, okay? Or if you prefer, is Rn itself, because they are isomorphic. Let's think about an open set. And so this means that U times Rn is a topological space, okay? In particular, you can say that an open set in your space can be just an open set here times Rn. Okay, so you are taking as open set the open set in your manifold, and over every point of your manifold you are putting all the vectors, all the tangent vectors that you can put on it. And you call this a fundamental system of neighborhood. You use these open sets to generate a topology on your union, on the big part. Okay? And this is giving the topology on your bundles. Let me check where it is. This.
For this reason, you need a chart.
Yes, yes. I'm working locally because to define a topology, I can work locally and then go globally in this way. So this means that, this is the meaning of the sentence. This means that we can use this map, that is the identification. You see, this is the point, these are the coordinates of the vector tangent at that point. And this means we can use this map to transfer the topology from here to the chart. This means that this is a chart. Okay, this means that for the space that I'm building, that is the union for P into M of the tangent spaces into M, a chart, a local chart around P, fix a point P, will be just the local chart of the manifold around P, chart around P, times Rn. This is the open set. And what is phi? Well, phi is the map going from this chart into Rn times Rn. In which way? Well, this is already Rn with the original phi. Let's say this is phi tilde. Okay, and this is going to Rn through phi. And so this map is just phi times, I guess, the identity. Yes, I think so. Okay. So these are the charts around a point. And would be a nice exercise to show that these charts, when they overlap, they are smooth. And you know why? Because when they overlap, on the overlapping, here will appear the transition function of the original manifold, which is by definition smooth. Okay.
The tangent spaces can be seen as a tangent subspace made of the cards that define the tangent vectors.
A single tangent space is actually a point times Rn. And so it is not open. In order to have an open set, you need an open set times Rn. Okay. Well, the definition is here of the tangent bundle. The tangent bundle is the union of all these tangent spaces made a differentiable manifold in this way with this atlas. Okay, here there are a lot of technical details I'm skipping, as you can see. Here there is the manifold structure. Here they are showing that the tangent bundle is Hausdorff, is a good topological space. So up to now, this is just topological space, topological manifold. And now they are giving the manifold structure. There is a lot to say, because I mean they are comparing a tangent vector and they are saying, okay, if I map these coordinates to this, when the two charts overlap, this transformation is infinity. Okay, and you see they are computing the transitions of this new defined atlas, and at the end it works. Okay, well, there is this general notion. What we are doing is very general, actually. We are taking, on every point, we are taking a vector space. You see, on every point, a vector space. On every point, a vector space. When you do this, we say you are building a vector bundle. Bundle means exactly doing what we were saying before. Something which is locally given by this U times Rn. This is the most primal way of giving a vector space over every point. Just take the product of the points times the vector space, the prototype of the vector space of dimension n. Okay? If you have a set, let's say E, that locally looks like this, then we say that you have a vector bundle. Of course, there are some more hypotheses. But that means a vector bundle is something such that on a point you have a vector space, and if you need to look locally, that space is just the product of an open set with the prototype of the vector space. Okay. Let me check if there is something more. Of course, there is a lot here to say, but okay. Oh, no, the point was in defining the vector. Remember, I told you the point is giving a notion of vector field as a map from U to this union of tangent space. Well, now we have this notion. Okay, now we know that the vector field is a map, remember, from, let's say, from the manifold on the union over all the point of the manifold of the tangent spaces to the manifold. This is what is called briefly the tangent bundle to M. Okay, so a vector field is a map from M to Tm to the tangent bundle. Now the tangent bundle is a differentiable manifold. And now we can say that the vector field is smooth if it is smooth as a map of between differentiable manifolds. Okay, but now we have to be more precise on the vector field is not only a map from the manifold to the tangent bundle. It's a very special map. Remember, at the point P, the vector field associates what? A tangent vector? Not a tangent vector and stop. Tangent vector in P. Okay, at the point P, the vector field associates a tangent vector to P. This means that if you go from the point P and you take the tangent vector x of P, and then you get back on the base by projection. Remember the picture, the open set, over every open set you have the vector space. This means that whenever you have a vector, you can project that vector on the original point. These are vectors over a point. So you have a notion of projection over the base. Okay, if you go back with this projection, you still obtain P. So this kind of maps into the tangent bundle are called sections. A section is a map in the tangent bundle such that when you get back, you are in P. And these are represented with this picture. Okay, this is the manifold. Over this, you have the linear spaces, which are the lines. Okay, and so a section means that to every point, you have a point over, you have a vector over this point. So you can't have that this point gives you a vector here. Okay, you have to have a vector over that point, meaning that if you go back, you obtain something here. So a vector field is, in this new language, a section of the tangent bundle. So now you should be able to understand this kind of language. Okay, section means just is the term we use to say that to a point P you associate an object over that point and not in another part of the manifold. Okay. Well, maybe we need the notion of frames for Lie groups. Well, you can have one vector field, right? That means on every point you have one tangent vector. But you can have two vector fields. That means on every point you have two tangent vectors. You can have several vector fields. You can maybe have n vector fields, where n is the total dimension. Then you can ask, are these vector fields everywhere linearly independent? If they are, you can say that these vector fields generate the tangent bundle. Okay? And in this case, you would say that these vector fields are a frame. Frame means a basis, but which is moving in some sense, because you have a different basis over each point. And of course, if these vector fields are smooth, and we are talking about smooth vector fields, of course, the frame will be smooth. So on every point, you will have a frame which is moving smoothly. I'm telling you this because maybe it will be useful for Lie groups. On Lie groups, we have a very nice frame. Okay. What's the time now? Okay, so I think we can stop here. And but if you have questions, please ask me while I go through.
Super dense lecture.
Yes, super dense. Sorry, and we made only.
Maybe even different insight on the vector bundle notion. So if you given the manifold as the distribution of particles with the particle moving on the manifold, the vector bundle is just like giving an internal space which represents the state of the particle at a given point. So one example, so I think this because one of the example of vector bundle you should method in is the passive space which would be one of the examples of synthetic manifolds data. So,
okay, it is called phase space in state space. Okay. Okay. In physics, there is an example of vector bundle that maybe some of you already encountered. That is the state space. The phase, spazio delle fasi in italiano. Sorry, guys. Okay. And you see there is a dedicated chapter to vector fields because they are very important. This vector fields chapter is the last one I was going to explain. Actually, we are missing an important part that probably Alberto will need, that is the local flow, the one parameters group associated with vector field. But I think it's time for questions now. And okay, questions?
Sorry, a quick one. You mentioned the frames at the very end. And you made an example x1, x2. These frames are meant at a given point, or considering all the manifold? So you can have frames considering
well, you can have a local frame. Usually when you say a frame, you assume it is defined on an open set. I mean, it's not defined just on a single point. Okay, but if you specify, you say a frame at a point, I wouldn't call it a frame, I would call it a basis.
Okay,
if you call it a frame, you're thinking to a moving frame. That means a frame with a point pointed in a point which is moving.
Okay, I see now. Thank you.
And if you have a global frame, that means for every point of the manifold, this is a very special kind of manifold. It's called a parallelizable manifold, because at the end, the tangent bundle, if you have a global frame, the tangent bundle is very, very simple. It's just the product of the whole manifold with the fiber, with Rn.
Okay, thank you.